In this video, I introduce a Swin Transformer, hierarchical vision transformer using shift windows. Vision transformer defines a global query and a pair of global key and value in input image, which has a quadratic computational complexity, so that the query can attend the global key distribution. VIT further splits input RGB image into non-overlapping patches, as shown here. Each patch is defined as a token that is a concatenation of the raw pixel RGB values, as shown here. Positional information is added to the tokens before the tokens are fed into VIT, as shown here. Hierarchical VIT applies a linear embedding layer on the raw valued features and then outputs C-dimensional feature vectors. The C-dimensional tokens are used as input to transform block 1 to output attend feature distribution, as shown here. To produce hierarchical representations, the number of tokens is reduced by patch emergent layers as the network goes deeper. A patch emergent layer concatenates the features of each group of 2x2 neighboring patches to produce 4-dimensional feature vectors, as shown here, which are used as input to the next transformer block 2 that outputs 2C dimensional features. The resolution of a feature map after 2 transformer blocks is reduced by 4 times. Window VIT limits the self-attention computation within local windows to reduce the computational complexity compared to the global multi-head self-attention computational complexity. Where H and W are height and width of the input image, and M by M is number of patches in a window. However, the window-based self-attention module lacks connection across windows, as shown here, because we define one group Q, key, and V for each window. To realize connections across windows, shift window partitioning approach alternates between 2 partitioning configurations in consecutive Swin transformer blocks. For example, output of the layer L is 2x2 uniform window distribution, as shown here. The input of the layer L plus 1 is a shift from output of layer L by half M and half M, which results in total 3x3 windows, as shown here, total 9. Swin transformer uses a shifted window approach to perform the local self-attention computation across windows, defined 9 groups Q, key, and V for each local window, as shown here. Number of shifted windows is increased, for example, from 2x2 to 3x3 due to the displacement of the 1/2 window size. Swin transformer uses a shifted window approach to rearrange shifted window distribution that has the same number of the windows as a regular distribution, as shown here, this regular uniform window distribution. And here we shift the window by 1/2 of window size. And then we move this A to here, and B from here to here, and C from here. And then we use same number of windows as a regular window distribution. And then this batch the windows are used as an input to the next transformer block. However, for these types of windows, we need use a masking cell for attention computation for each sub window. Due to manually adjusting the feature maps, Swin Transformer introduces a relative position bias B to each self-attention head in computing similarity, as shown here. We add B inside the softmax function. From an M by M sized window, the relative position along each axis lies in range from a negative m+1 to m-1. And the smaller size, the bias matrix is defined as here. The values in B are taken from a B hat. The detailed processing is shown in this figure. For more details, please check with these references. Thank you. Bye.